So in this problem we have a brick that's being thrown vertically upwards with an initial speed of 3 meters per second from a roof of a building. If the building is 78.4 meters tall, which is a pretty tall building, how much time must pass before the brick lands on the ground? Now, first thing I'm going to do with this problem is draw it, because it's kind of a little bit lengthy and there's parts to it. So starting off with the drawing is probably the best thing I can do. So first thing is I've got a building. Okay? And on top of that building I have a person, and that person is going to throw a brick upwards at 3 meters per second. Okay? After a period of time, that brick is going to reach its apex and then come back down. Okay? Now, what we're trying to do is we're going to try to solve for the time it takes to get to the top and then get back down and then all the way down to the ground. Okay, so we need to figure out how to get all that time together. The first thing I'm going to do, I'm going to draw a table to keep track of some information. Okay? So I'm really interested in two motions, two parts of this problem. The first part to get to the top, and then the second part to get all the way to the bottom. Okay? And to do that, I'm going to create two separate tables. Okay? One of them, I have an acceleration, velocity initial, velocity final, position final, position initial, and the all-important time. Now, because this problem is a simple free fall problem, which means that it's on the surface of the Earth, the acceleration in every section of this is always going to be down at 9.8 meters per second per second. The acceleration is always going to be down at that rate. So to express that, I've got a negative 9.8 meters per second, negative 9.8 meters per second. Okay, now the initial velocity is being thrown up at a speed of 3 meters per second. So arrows pointing down are going to be negative. Arrows pointing up are going to be positive. So that's going to be 3.0 meters per second. I will know this term in a second. I'm just not going to talk about it real quick. Now, V final. V final is going to be V initial for the second part of this motion. Now, you may think that there's not enough information in this problem to solve for V final, but it's my problem. I get to decide a lot of things in this problem, and what I'm going to do is I'm looking for the point where the brick gets to the very top of that motion and then starts falling down. At that very top of the motion, the velocity final has to be 0. It has to be 0, because if it's not 0, then it's going to continue to climb upwards. Okay? It has to stop and then turn back around. So that and that are both equal to each other. I don't know what this is, not yet. The final position, I don't know. My initial position, I do know. It starts on the top of a building. Now, there's a couple of things I can do. I can say that this point is going to be my 0 position. This is where everything is measured from. Or this point down here is my 0 position. Okay? Either one of them will give me the correct answer. What I am going to do is I'm going to say that this is my 0 down here. And up here is going to be the height of the building. And that was 78.4. Okay? I don't know. Well, I do know its final position to be 0. I don't know what its initial position is. And I certainly don't know any times. So I've got a lot of question marks floating around. Now, what I need to do, I need to be able to get this final position for the initial position of this. And I need to get the time. So what I'm going to do is I'm going to look at all my equations, and from this table, the information I have, I'm going to try to get these last two bits of information. So the first one I have is final velocity is equal to initial velocity plus acceleration times time. I also have my final position is equal to initial position plus initial velocity times time plus 1/2 my acceleration times squared, and then my time independent equation, v final squared minus v initial squared is equal to 2 times my acceleration times my change in position. Okay? So, going through this first list to see if I can fill this out. Do I have final velocity? Yes. Initial velocity? Yes. Acceleration? Yes. So I can solve for time really quickly. How about this one? Well, final position, I don't know. My initial position, I do know. My velocity initial, I don't know, or I do know. My time, I can solve for it up here, so I should have that. So it looks like I can solve for final position in this one if I solve for time in this one first. And then looking at the last one, my time independent one, v final, I do know. V initial, I do know. My position, or 2 is 2. Acceleration, I do know. My final position, I don't. My initial position, I do. So I can find my position without time. I can find my time without position. And then this one I can use if I need to fill in any gaps. Okay? Cool? So the first thing I'm going to do is I'm going to solve for the important one. We're looking for time in our answer, so we're going to start with time. Or this one. Okay? I'm going to erase all the other equations and just start filling in numbers. Alright, so we want to solve for time, so I'm going to move everything over. I've got 1, 2, 3 terms. I want to get that to all my terms except for one on this side, so I can solve for that. So what I'm going to do is I'm going to bring over this term right here. And then I'm going to isolate the variable that I'm looking for, and I'm looking for time. So I'm going to divide out A. So I'm left with v final minus v initial divided by A is equal to t. Okay? So my final velocity was 0, my initial velocity is -3, and my acceleration is -9.8. Now, normally in my class I would say that the acceleration is -10. I'm going to just treat it like that. Okay? So v final, so that was 0 minus 3.0 meters per second over 10 meters per second per second. Okay? That is equal to my time, so I'm left with 3 over 10, which is, just to be complete, approximately 0.3 seconds. Okay? So my time for the first bit of motion is 0.3 seconds. Now it's an approximation because I said that this was 10 and not 9.8. So if you get a different number, it's about the same. Don't panic. It's not you, it's me. Okay? Now, what I want to do from here is I want to solve for that final position. Now, the reason why I have to solve for that final position is I need to know how far it's going to fall. Okay? So now that I've got my time, I'm going to erase this, and I'm going to solve for my final position. Okay? And I'm going to use the time independent one. If I have a choice, it's usually the first equation I do use. So rewriting that equation, it's v final squared minus v initial squared is equal to 2 times my acceleration times my change in position. Okay? I'm looking for my final position, so I need to move everything else around. I'd like to be able to move this first, but I can't because of the parentheses, so I have to move this first. So I'm left with v final squared minus v initial squared over 2a is equal to, get to drop the parentheses because it's not being multiplied by anything anymore, And now I need to just simply drop the parentheses. Now I just need to move over the initial position to find the final position. So that goes to V final squared minus V initial squared over 2A plus XI equals XF. Initial position, final position. Okay? Math gets simple because this term turns out to be 0, so it goes away. And I'm left with my initial velocity squared, so 3 squared. There's a negative sign out front. It's not negative velocity, it's negative the term. So that's going to be negative 9 divided by 210. 2 times 10. So rewriting that real quick, I shouldn't have gone off on that tangent, but I'm going to clear this space off so I can use it. Okay, so I'm left with negative 9 on top, okay, meters per second squared divided by 2 times A. Now 2 times, and once again the answer is 9.8, but what I'm going to do is just use negative 10. Okay? So I have a meter squared per second squared over a meter per second per second. That cancels off my seconds. It cancels out one of my meters. So I'm left with negative 9 over 2, well, let's just say 20, negative 20 meters plus my initial position, 78.4 meters, is equal to my final position. Now, this positional value right here is just simply how high it gets over the top of the building. This is, well, we're taking our position not to be here, but here, so I have to account for all that additional height I started with. Okay, so you can hopefully see why I can set this point at any point and it won't make a difference. Okay, so let's just round this up to 10 and say that's about a half. Okay, negative terms cancel out. This is about 10. About 10 over about 20 gives me about 0.5. 0.5 to this gives me about 79. So the final position is about 79 meters above the ground. Okay, really quick, I said this was about 10. That makes about 10 over about 20, which is 2, or not 2, 1/2. 1/2 plus 78.4 gives me 78.9, about 79. I mean, I'm just making some approximations just to get through the math quicker. Okay, so that means my final position is 79 meters, which turns out to be my initial position, 79 meters for the second part of the problem. Now, here's the really cool thing about the second part. We only need one bit of information. I don't need to solve for the final velocity when it hits the ground. That's not important to me. I may find it interesting, but the only thing I'm looking for is time. So what I have going on for this second part of the problem, I've got my table again. I'm going to go ahead and write down my equations and see if I can find time. V final equals V initial plus AT. Position final equals position initial plus V initial t plus 1/2 AT squared. And V final squared minus V initial squared is equal to 2 times X final minus X initial. Now this one is automatically eliminated. And the reason why it's automatically eliminated is there's no time. I'm trying to solve for time. So this one clearly will not work. Okay, so I won't even bother talking about it any more than I already have. So final velocity I don't know. Initial velocity I do know. Acceleration I do know. Time I don't know. So there's 2 variables in this equation. So it doesn't look like a good candidate for me. So let's look at this one. Final position I do know. Initial position I do know. Initial velocity I do know. Time I don't. Acceleration I do. So this looks like a great candidate. So it looks like I'm going to get to use all 3 of my equations on this problem. Okay? My final position, well, we say it hit the ground. My initial position, it starts up really high, plus the initial velocity. This is a really great thing because this term is 0. So this whole thing goes, or this variable is 0. So this whole thing goes to 0. Plus 1/2 negative 10 t squared. Okay? 79 goes to the other side, goes negative 79 meters, is equal to 1/2 negative 10, oh, look at that, forgetting my units, t squared. Okay? Half of 10 is 5, so I'm left with negative 5 over here. So I've got negative 79 meters is equal to negative 5 meters per second t squared. I bring this term over to the other side by dividing it, and that's about 80. So 80 divided by 5 is going to give me, well, let's do it. So 80 divided by 5, that goes in once, 3, so it's about 16. Okay, which is great. I need it to be a nice simple number. So 80 divided by 5, that gives me 16 seconds squared is equal to t squared. Now the negative signs do cancel each other out. I didn't really tell you that. Looks like you can't see that, so I'm going to go ahead and move that over to just right here. 16 seconds squared is equal to t squared. Take the square root of 16. That means 4 seconds. So my time for the second half of motion is 4. So my total time, the amount of time it takes to go here, up, and then back down, is going to be this 0.3 plus this 4. So my total time is going to be, not a very good T. Total time is going to be 4.3 seconds. And that's an approximation. I've made a lot of approximations when I solved this problem. So your number could be different than this, but not drastically different. Maybe 5, maybe 3, but nothing more than that. Okay? Cool.